Next step on the acid-base chapter is, well, we've been talking about the nature of acids and bases, what they are and how common they are in everyday life. But now, if we want to be more specific, well, what's an acid? What's a base? And how can we recognize those? So far, we have enough information on a carboxylic acid, what we are looking for when looking at those organic compounds. But in terms of a classification of acids and bases, how in general you will identify an acid and a base? How would you define any of those compounds? And to do that, there are three main theories. And here, the most common one, well, not the most common one, the oldest one, is the Arrhenius definition. Okay, it's a simple definition. It's pretty much an acid. It's something that can provide you with hydronium ions, and a base is something that provides you with the hydroxyl ion. Okay. Here we can call this simply hydroxide. Well, actually, simply hydroxide, or you can also call it the hydroxyl. Not like that. Let me rewrite this. The hydroxyl ion. Okay, pretty much is acid give you H3O plus, and bases will give you OH minus. Okay, and it's kind of self-intuitive that these substances need to dissolve in water for them to be able to provide with that hydronium or that hydroxide. Okay, however, this definition is a little exclusive in terms of not. There are few substances that still can be considered acids, but if you look at the Arrhenius definition, you probably wouldn't consider like acids. So the next theory that is a little more extensive in terms of what you can consider as an acid or a base is the Bronsted-Lowry definition. By far, this is going to be the most common definition that we're going to be using in our discussion of acids and bases. And it pretty much describes, if we said at the beginning of the chapter that an acid-base reaction is a transfer of hydrogen atoms, hydrogen ions for that matter, then Bronsted-Lowry is telling you that an acid will donate protons or hydrogen ions, and a base will accept. So now we are not limiting our definition of a base to something that will provide you with hydroxides, but with something that will accept those protons. So if the acid is providing, and don't get me wrong, the acid definition of Bronsted-Lowry is pretty much the same as Arrhenius, something that will give you or that will increase the concentration of H plus in solution. But for bases, it's a little bit different, because now a base is something that will accept that proton. Where is that proton coming from? It's coming from the acid. So there is the acid-base reaction. It's the transfer of that proton. And then we have this is a little more difficult to understand, but the Lewis definition is is wider definition. Okay, there are things you are not limiting the acid-base reaction to the process of just transferring a proton. It's going beyond. It's considering the acid-base reaction as a not exactly transfer of electrons, but interaction of substances that are in need of electrons with substances that have excess of electrons. Okay, it's not necessarily ionic substances that we are talking about here. We are just talking about there are some compounds that will be deficient in electrons. For example, the H plus is deficient in electron. Okay, it has a positive charge. Technically, that hydrogen wants to complete 2 electrons in the last shell, so it's in need of 2 electrons. Okay, but we're gonna leave the Lewis definition for last because that's a more conceptual approach that we're gonna take to acid and bases. We're gonna do a lot of calculations, and those calculations will have to do mostly with the Bronsted-Lowry definition of acid and bases. So again, the Arrhenius theory. Acids is anything that will increase the concentration of H plus in solution. So if you have this acid HCl, when you put that acid in water, it will split in two, so to speak, and you will obtain your H plus. Okay, so in a solution of an acid, according to Arrhenius, you will have a mixture of hydrogen ions and the corresponding anion from that acid. On the other hand, if you have a base, then the base will increase the concentration of OH minus in solution. Technically, according to Arrhenius, the base itself must contain the OH minus. Okay, so that's the limitation in Arrhenius theory. This ion here must be contained on the base. So that's the source. Okay, so that's technically the main limitation of the Arrhenius theory. So once again, according to Arrhenius, the acid will increase the concentration of H plus in solution. H plus, remember, if we are talking about acids and bases, we will consider H plus and hydronium ions interchangeably. If you are referring to H plus, I'm going to assume that you are also referring to hydronium. If you are referring to hydronium, I'm going to assume that you are referring to H plus. So it doesn't really matter to me. Technically, the hydronium ion is more correct because the H plus does not exist isolated in solution. But for all practical purposes for this class, you can assume those two are equivalent, are perfectly the same. So you can refer in terms of one or the other. But if you do so, I would ask you to keep consistency. If you prefer to just refer to H plus, keep that for the whole semester. Okay. If you want to refer better to hydronium, then keep that for the whole semester. Okay, just to be kind of consistent in that regard. So now the acid-base reaction. Okay, and this is according to Arrhenius. So Arrhenius is telling you, well, if an acid provides or will increase the concentration of H plus and the base will increase the concentration of OH minus, then the acid-base reaction technically is the reaction between those two ions. So basically what you are looking at is H plus plus OH minus. That will give you H2O. So according to Arrhenius, that's your acid-base reaction. For the most part, if you are doing any acid-base reaction here and you are looking at what the net ionic equation is, that would be it. H plus plus OH minus, that gives you water. So now the neutralization reaction, okay, because this is the acid-base reaction, right? But this is the net ionic equation. But when you're performing these reactions, you are not just adding H plus to the solution, you are not just adding OH minus to the solution. They are coming from somewhere. They are coming from an acid in the case of the H plus, and they're coming from a base in the case of the OH minus. So that's what you have here. In general, if you want to picture the acid-base reaction, well, your reactants are an acid and a base. Okay, so the acid is the source of H plus, the base is the source of H minus. Okay, these two will give you water, and the leftovers from the acid and the base will give you the salt. Okay, so pretty much what we are saying here is that if you have the acid and the base, this proton here will react with the OH minus to produce water, and the anion of the acid will react with the cation of the base to produce the salt. Okay, so that's pretty much what we are doing here. So, and this is, if you can also see it this way, you are switching ions here. Those two and those two, and that's how you obtain your products in the reaction. So what is the problem with Arrhenius? Why is not such a good theory? I mean, it for the most part you can identify a good number of acids and bases, but for example, we have this substance that is very common, ammonia. And in the structure of ammonia, well, that is not oxygen. And if you don't have oxygen, there is no possible way that if you start with NH3, that out of the structure of that molecule, you cannot get OH minus. However, ammonia is a basic compound, basic not because it's simple, but because it's a base. And actually, if you have ammonia and you add it to water, the result is the OH minus increase in solution. So there is something else going on there that makes ammonia a base, even though it doesn't have the OH minus in their structure. So it cannot provide it itself, okay? However, OH minus will increase. The concentration of OH minus will increase if you add ammonia to water. Now here, another thing for ionic compounds. Okay, you have sodium carbonate, for example, or sodium oxide. You have these two here. They don't have hydrogen, right? They don't have OH minus, and still they are able to increase the concentration of OH minus. So these two, the carbonate and the sodium oxide, even though they also don't have OH minus, they can also cause the concentration of hydroxide ions to increase if you add them to water. Again, that goes for bases, but for acids, you have CO2, right? And CO2 doesn't have hydrogen, and you would hardly consider that an acid. But if you dissolve CO2 in water, you will end up with an acid solution. And why that happens is because there is a reaction between the CO2 and the water that produces carbonic acid. So CO2 itself, you will not consider an acid because of Arrhenius, but if added to water, will increase. This will make the concentration of H plus to increase. Okay? And of course, for Arrhenius, it's vital that the reaction, the acid-base reaction, occurs in water solutions. But there are some other reactions that can perfectly happen out of the aqueous world. Okay, so if you don't have an aqueous solution, technically, the Arrhenius theory will fail miserably explaining an acid-base reaction. That's why we need something else. So Arrhenius is a good starting point. It will identify acids and bases very quickly, but it fails at identifying whenever you have substances that still behave an acid or a base, but that have the requirements for Arrhenius. Okay, and those requirements are to have H plus or OH minus in their structure. So that's when we have Bronsted-Lowry. Now, Bronsted-Lowry is a more general description of acids and bases because now we are focusing our attention only on the proton. Okay, and because of that, we don't care anymore about the acid or the base having that proton or having the hydroxide. Now we care about, we kind of narrow our point of view to that hydrogen ion, and the acid for Arrhenius would be that one that will make the concentration of H plus to increase in solution. It doesn't matter if the acid is provided the H plus itself, but if that substance, dissolving that substance in water, will make the concentration of H plus increase, then that would be considered a base. And in the other hand, if you have a base and you don't have an OH minus in the structure of that base, but still dissolving this solution, this substance in water will increase the concentration of OH minus, then that is a base. Okay. So if we want to summarize this, according to Bronsted-Lowry definition, let me change the color of this. An acid will make the concentration of H plus to increase, and a base will make the concentration of OH minus to increase. But they don't need to be the sources. Don't need to be the source. Okay, they can, but they don't need to be. So that's the main thing with the Bronsted-Lowry acid-base theory. And we want to use a specific language here. For an acid, we refer to an acid as an ion donor, and for a base is a H plus ion acceptor. That doesn't have to do, that actually doesn't affect the fact that you are increasing the OH minus concentration. That will make more sense as we move through the chapter, but as of now, the bases still have to do something with the hydroxide ion, but in terms of Bronsted-Lowry, the base is there only to capture that proton that is coming from the acid. Pretty much, in a nutshell, that's what's happening here. So now, if we want to take a look at the acid-base reaction according to Bronsted-Lowry, you still have an acid, you still have a base as your reactants. There is a transfer of this proton from the acid to the base, so that in the next, in the other side of the reaction, well, you still have the proton, but now the proton is attached to the base. Okay, so in the reactant side, pretty much the proton is attached to the acid. On the product side, now the proton is attached to the base. And then this is a specific language that we use with the Bronsted-Lowry theory. And you have to get very familiar with this and be able to identify which one is which. You have the conjugate base, and then you have the conjugate acid. Now, when you say this, the conjugate base and the conjugate acid, okay, you have a conjugate base. Is the conjugate base of what? Is the conjugate base of the acid, and the conjugate acid is the conjugate acid of the base. So they are, you identify them in pairs. Okay, so an acid will not have a conjugate acid. An acid will have a conjugate base. Therefore, a base will have a conjugate acid. Okay, so it's very important that you match these pairs correctly. And let's write that down again. Let's use blue here. The pairs, the conjugate pairs, let's put it this way. You have the acid and the conjugate base. and you have the base and the conjugate acid. Okay, do not cross associate these two. Okay, there is no such a thing as acid with the conjugate acid or the base with the conjugate base. They go the opposite way. It's an acid with a conjugate base. It's a base with a conjugate acid. This is very, very, very important. Very important that you are able to recognize this. So here Bronsted-Lowry acids will be H donors, H plus donors. Okay, so and they don't really need to provide the H plus themselves, but they will still going to be a donor because they will increase the concentration of the H plus in solution. Okay, so in this case, if you have acid, hydrochloric acid, this hydrochloric acid is transferring a proton to the water molecule, and then you end up with hydronium ion here. So if you are looking at the concept of conjugate pair, then is HCl the acid with Cl minus, that's the conjugate base. Okay, this is the conjugate base, and this is the acid, of course. And the other pair would be H2O, H3O plus. Okay, so this is the base now, and this is the conjugate acid. Okay, and the important thing here is that these two are together, and these two are together. Okay, so those are the pairs in the according to the acid Bronsted-Lowry acid-base reaction. Now with Bronsted-Lowry bases, they are proton acceptors, and in this case what we are looking at is that one of these protons of the water will be transferred to ammonia, so that now ammonia has not 3 but 4 hydrogens in the structure. So if we do the same thing, this is your base, this is your acid, this is your conjugate acid now, because you are getting that out of a base. So it's the conjugate acid, and this is the conjugate base. Okay, so once again, these two are together, these two are together. Okay, those are the conjugate, the acid-base conjugate pairs, okay, that you have in each case. Now, one thing interesting here is that water, in this case, was a base in this reaction, but in this one, water is an acid. Okay, and I want you to keep that in mind. We will get to that early enough, but I want you to notice that their water is having a dual behavior. It won't have the dual behavior at the same time, but it will depend on what substance you are combining water with. Okay, if you're combining with an acid, then water is going to be the base. If you're combining with a base, then water is going to be the acid. So keep that in mind for now. So in summary, and whenever you have acid-base reactions, it doesn't really matter what is the structure of the acid, what is the structure of the base. We can oversimplify that reaction to identify the conjugate pairs here. Okay, all we care is about this proton, that hydrogen ion. In one side is going to be attached to the acid, in the other side is going to be attached to the base. Okay, and when it's attached to the base, then it becomes a conjugate acid. And that, again, it's really important that you kind of understand that. And because we are having this situation here, okay, it doesn't matter the acid, you can always simplify that to just A to refer to the acid. And this is the anion of the acid, which is the conjugate base. And when you have the base, this is the cation of the base, which is the conjugate acid. Okay, and for the most part, these are acid-base reactions that can be perfectly equilibrium reactions. Why? Because if it is a proton transfer reaction, and in one side you have the proton attached to an acid, and in the other side it's going to be attached to the base. Well, if we invert that reaction, what do you have? Now you have a base and you have an acid, and pretty much the reaction can be reversed, because they will still behave as an acid and a base, and an acid and a base, when put together, there will be a transfer of a proton. Okay, so technically this proton can go back to the conjugate base of the acid. So again, here there is the opportunity for the acid-base reaction to be an equilibrium reaction, and it will depend on what type of acid, what type of base you are having here. And by that I mean whether you have strong acids or bases, or weak acids or bases. If they are weak, it's going to be equilibrium reactions. If they are strong, then it's going to be pretty much a one direction reaction. Okay, did I say that it was really important to be able to identify conjugate acid-base pairs? Well, here is more of it. Okay, so remember, when you have a base in a reaction, an acid-base reaction, the base will accept a proton and will become a conjugate acid. Okay, once the original base accept that proton, it's not a base anymore. It becomes a conjugate acid. And a conjugate acid will behave as an acid. Okay, so that means it will be able to transfer that proton back. In the case of the acid, once that proton is gone from the acid, then it will become a conjugate base. Think in terms of, once the acid releases that proton, then it becomes proton deficient, and so in a way it wants the proton back. So it's a conjugate base because now it's able to accept that proton back. Okay, and whenever you have this situation, okay, for example, for a base you add hydrogen, you have the conjugate acid. For an acid, you take the proton out, then it becomes a base. They become a conjugate acid-base pair. And one thing that I want you to notice here, because that is going to be the easiest way to recognize conjugate acid-base pairs. I may ask you to tell me, if I give you a pair of compounds, can you tell me if that can possibly be a conjugate acid-base pair? And the way to recognize that without having an acid-base reaction is that there will be potentially a conjugate acid-base pair if formulas differ only in one hydrogen. For example, you have NH3 versus NH4, right? So can that be a potentially acid base conjugate pair? Well, absolutely. There is a difference of one proton between them. Which one is going to be the conjugate acid? Which one is going to be the base, so to speak? Well, the one with more H plus, or the one with more hydrogens will be the acid. So this is the acid, this is the base. When you look at the other side, you have water and you have OH minus. Okay, likewise, this one is the acid, this one is the base out of that conjugate pair. Why? Because water have more hydrogens than the OH minus. Okay, so that's pretty much what happens here. And remember, it's always the transfer of that proton. This acid-base reactions is all about the transfer of protons. Okay, if the proton is leaving, the substance the proton is leaving from is the acid. The substance the proton is going to is the base, pretty much. Okay, and they once the reaction is over, in terms of once you are looking at the products, then the roles are reversed. Okay, roles reverse, which means if in the reactant side you have a base, when you are in the product side, the base is no longer a base but an acid. Okay, so that's what I mean by the roles are being reversed. So the roles changed after the reaction goes to the product side, and it can go back. Okay, but now the base will behave, because the base became a conjugate acid, it's now going to behave as an acid, and because the acid became a conjugate base, then it will behave as base. So the transfer of the proton will be in a different direction. So how about we have this problem and we want to identify which one are what are the acid base pairs, right? So let's write the first reaction. So we have H2SO4. For now, everything is in solution, so let's forget about the stage for now. H2O that goes to HSO4 minus plus H3O plus. So think in terms of, well, we are looking at sulfuric acid, and of course this is an acid, and if this is an acid, then water is a base. So, but if you didn't know, how would you know what is the role of a sulfuric acid here? Well, you take a look at the other side, and then you see HSO4, and the difference between these two is that there is a difference of one hydrogen. Which one has the most hydrogen? That would be this one. Therefore, that's the acid, and this is the conjugate base. What happens to water? Water has two hydrogens here, has three hydrogens on the other side, that's the hydronium. Therefore, water is the base, and this is the conjugate acid. Okay, so pretty much that's it. And these go together, and the H2SO4 with the HSO4 minus go together. In the other reaction, we have HCO3 minus plus H2O that goes to H2CO3 plus OH minus. Okay? Now, what happens to the first substance here? What happens to this one? It has one more hydrogen there, therefore this is a base, and this is the conjugate acid. And what happens to water? Water has two hydrogens here, only have one here, therefore this is this is the acid, and this is the conjugate base. So it's pretty simple. If you can recognize what is happening here, with those substances, then it's pretty easy to understand what's going on. So one more here, more about identifying. So let's write the first one, C5H5N plus H2O that goes to C5H5NH, one more hydrogen, plus OH minus. And there is no need to be scared when you see something like this, because when you identify that these are, think in terms of the H of the proton, right? So this can perfectly be B plus H2O that goes to BH plus OH minus. And you can perfectly explain that reaction in terms of the base being B. Okay, that you are not missing any information here. This is just you are trying to make your life easier. So therefore, this is the base, this is the conjugate acid, and this is the acid, and this is the conjugate base. Last but not least, you have HNO3 plus H2O, and then you obtain H3O plus. These two go together, plus NO3. These two go together. So this is the acid. You have one more hydrogen there than here. This is the conjugate base. And of course, then this is the base, and this is the conjugate acid. Okay, at the beginning might be a little confusing, but this is pretty, let's say, standard definitions, and it's just about, if you are identifying conjugate acid-base pairs, then you are looking at similar structures, similar formulas that are differing in only one proton. So if you compare HNO3 versus NO3 minus, is one proton, one hydrogen difference. If you don't know absolutely anything about this, the one with the more protons or more hydrogens is the acid, and therefore the other one is going to be the conjugate base. Or let's forget about the conjugate base here. This is simply the base, and these two we name it a conjugate pair, because their roles are going to be different depending on in what side of the reaction they are. Okay, but they are an acid-base conjugate pair. That's the important thing to remember. Okay.